remember we have this word goodness of fit. We want to know, what is this all about? And actually, I got through the first slide last time. The definition of a goodness of fit test. So what is it? It's a test. You're testing a hypothesis, so we're used to that by now. That an observed frequency distribution, and I went over what that means, fits some claimed distribution. You guys gave me a bunch of examples, okay? But I didn't at all get into how to do it yet, so we're gonna talk about that today. How do you figure out if you have data and you say, hey, I think this is a normal distribution, or I think this is something else? How do you check to see if it really is or not? Well, that's what's called a goodness of fit test. So, notation we need. Because here's some things you haven't seen before. This big O. O is going to be what's called the observed frequency of an outcome, as opposed to E, which is the expected frequency of an outcome. All right? Now, O is based on data. E, when we say expected frequency, that's based on probability. Right? Now, by the way, do you think that O equals E ever? No? Yeah? No? Yeah? Do you have a reason why you think that? So, Kate, you think no or yeah? Okay, because why? Yeah. Okay. David? Could happen. You don't want to say never. Okay. Yeah. Okay, so maybe we don't want to say never, but maybe we want to expect that usually, as Kate's saying, you know, your observed frequency, that could change. But what you predict, that's based on some formula, right? We have lots of ways of computing probability that we studied. And so we're going to see those coming back, I guess, when we go to compute E. Now, yeah, this section they're going to use the letter K to be the number of different categories or outcomes. All right? And we'll show you an example of that soon. And this is familiar. N, number of trials, right? Sample size in a sense. Okay, we've had that plenty of times. Now, like any other thing we've done, you need to know there are requirements. What are they here? Data have been randomly selected? Yeah, of course. The sample data consists of frequency counts for each of the 5 categories. Or each, why did I say 5? Each of the different categories. Okay? So what is the data? Frequency counts. Okay? That's what we're measuring. Well, we've been doing that a lot. How many of this? How many of this? How many of that? Now, requirement 3. For each category, the expected frequency is at least 5. I don't care what you actually observe, but the expected frequency should be at least 5, or else we really shouldn't do a goodness of fit test for that category. Okay. A brand new test statistic. And this is almost the only reason I'm covering this. It's not the only reason. In some sense, section 3 of chapter 11 is probably one of the things you may come back to. I know, because I was a biology major for 2 years before I switched to math. And the first statistic that I remember we used regularly was this one. Do you guys know this Greek letter? It's called chi. So this is the chi-square statistic. Anyone ever seen chi-square before? One? Yeah, when I was a biology major, I remember taking a course in genetics, and we worked with this a lot. And even in some of the other biology courses, this was an important statistic. But it's used, for example, to do a goodness of fit test, and we're going to use it for something else later. And actually, you may remember, this guy appeared earlier in the book, and we skipped it. Do you remember that? What was it for? For variance, right? Remember we were doing some estimating? Anyways, we'll leave that go. But anyways, here's the statistic. Oh, by the way, one confusing thing. Chi is a Greek letter, but it is a statistic. Usually, when you have Greek, what does that mean? That you have the population, you have parameters, right? Well, people have been using chi for so long for this statistic, chi-squared, they just leave it. We're not going to make, not going to turn it into our x, because we just don't. So you just got to deal with that. That's a statistic. What is it? Well, this says we're going to do what? Add up a bunch of stuff. What are we adding? Well, we're taking O minus E. What is that? That's the difference between what? Observed and expected. Now, that's what we're measuring. We're measuring how much is the observed value deviating from what's expected. Okay? And then, why do we square it? Yeah, we want everything to be positive. We don't want these differences canceling each other out. We want to measure all of them. So just like you did when you did standard deviation. When you do this chi-squared statistic, same idea. We're going to square it. And yeah, that's why we write chi-squared also. And is that you may want to take the square root at some point. I don't think we will. But and then we divide by the expected to get sort of an average, if you want. All right. But anyways, I guess all you really need to know is that this is the formula. Because if you know that, then you know what to do, right? We take a test statistic, and what do we usually do when we're doing some kind of a hypothesis test? We compute the test statistic and then do what? Get the p-value. You get the p-value, then what do? Well, the p-value came from, this is the z-score in a sense, right? Although it's not going to be z, it's going to be chi-squared. But you get the p-value, reject or accept what? The null hypothesis. Now, I didn't tell you what the null hypothesis is yet, so that's kind of where I'm leading. So let's go there. Oh, remember this? Critical values. What are critical values? Well, you're going to have a significance level again, right? What's the significance level? How do we do that? What letter? Alpha equals, for example, maybe 0.05, for example. And then the picture is, well, you have a distribution. Now, it says that goodness of fit hypothesis tests are always right-tailed. When you look at the graph of a chi-square graph, it's squiggly and then straight. It looks like this. Actually, it kind of looks like the curve that you use when you make the chi symbol. It's right-tailed. That's the data. Okay, so the data kind of looks like that. And when we say we're going to find the critical value, what we do is we figure out what's the value here so that we can get, guess what this is called? Critical region. And then I'm going to graph my test statistic. And suppose my test statistic is here. Then what do? then we leave it, let it fly, right? But if the test statistic is here, that's when we reject. Okay, so this is, same idea is coming back. It's a different distribution. And you need to know what the hypothesis is that you're testing here. Oh, one other thing. Remember the old degrees of freedom? You will find on that pull-out card, table A4. I think it's the only big one on there we haven't used yet. So actually, I will pull that out for you. But just as we had when we did, say, the student t-test, you have different shape distribution depending on your number of degrees of freedom. And last time it was n minus 1, right? Well, here we're going to use k minus 1 degrees of freedom. Now, what was k again? Number of categories. So I have to show you the example so you see what categories are. But then I look and I have this huge, list of p-values. Well, it says area to the right of the critical value. So basically, this is going to be the area of the critical region. And then that'll tell me, how much area I have in here. Okay, the red. So we'll use it. We'll show you an example how to do this. Oh, it says that you can get p-values from computer software. TI-83 works fine. Or 84 works fine for this. So I'll try and walk you through that today also, if you have your calculator. Or you can just use table A4, either one. Now, how do we compute E? We can always compute using the formula E equals n times little p. All right, so wait a minute. What is n again? Well, E is the expected frequency, right? Number of trials. And P, what is P? P is going to be the probability. Remember I said that E is computed based on a probability? And I see a typo here from our editor, so I'm going to edit it myself right now. It says if all expected frequencies are equal. I guess I don't really like that. I'd rather say if all the probabilities are equal. Or if all categories are equally likely. That's what I like. Then you can use this formula. This is also in your book, but I wasn't sure that they explained very well how to get it. And people worry when they have more than one formula. That's what I'm worried about. That's why I said you can always do this. Just take the number of trials times the probability of, well, each trial, in a sense. Times the probability of being in that particular category is what I should say. So, for example, suppose I have 3 categories. What are they? I don't know. Gold, silver, and bronze. This is a very dumb example, but it might work. All right. Suppose I tell you your chances of getting a gold, a silver, or a bronze, it's equally likely. Well, then what's the probability of getting any one of those? 1 out of 3. So when I go to compute what I expect, if I have 5 people, now let's say 6. If I have 6 people competing, and they're all equal, everybody's going to get a medal, right? I should get 6 out of over 3, which is 2. I should get 2, 2, and 2, if n equals 6. Does that make sense? How do I get it? E equals 6, which is n, times what's the probability of each one? 1/3. So to me, that's the same as this. 6 times 1/3, or 6 divided by 3. Now, sometimes categories are not equally likely. Maybe you have a situation where you say, I'm going to give 1 gold medal out, I'm going to give 1 silver medal out, everybody else gets bronze. Well, that would be this kind of situation. Right? So then we'd say, oh, the probability of getting a bronze is 4 out of 6. Yeah. Jim. That's right. Yeah, I mean, we're trying to say, what do we expect to happen based on probability? And before I get David's question, one more comment. We've had the word expected before. Expected what? Expected rhymes with value, but that's not a word. Remember that? Expected value? So when we had expected value, we had a formula for it. I don't know if you remember this. The expected value of a random variable x is the sum of the x's times the probability that x is x. We had a formula like this back in chapter 5. It said, hey, take each x and multiply by the probability. Well, that's really what you're doing here. You're taking n times the probability. So it's not something we haven't seen before in a sense. Let me cross that out because that's not what we're doing right now. Okay, who had a question? David.
For the equation you did,
Yep.
would you read that as like 6 times 1 over 3?
Yeah, 6 times 1 over 3.
What equation are you using?
Right above. N is 6, and the probability of any one of those is 1/3. So that's why I expect 2 gold, or 2 silver, or 2 bronze in that situation. Okay.
So you were doing that in the 6 times 4 out of 3 for the bronze in the second example?
Yeah, so I guess here, well, so for example, how many bronze do I expect? Yeah, I guess it'd be 4 times 1 out of 3. No, I'm sorry. No, I did that wrong.
6 times 4.
6 times 4 out of 6, which is 4. I don't know. This is not a good, remember I said it might be a good example? This is not so good anymore. We'll see it later. Okay. Yeah, that's what happens when you make them up on the fly. Okay. Let's go away from that. Now, this slide here states some things that I think will make sense to you. I don't think it's worth writing down, but I do think I left the slide in because I think it's worth talking about. Now, when we say a close agreement between observed and expected, what I mean is O minus E is small, right? They're close together. Or maybe what I should say is O minus E squared is small, right? When you square it, it's still going to be small. It'll be a small positive number. If the O and the E are close together, look what happens. Chi squared is small, but that means you have a large p-value. Why? Because here's the picture. Remember, that's what chi looks like. And if you have a small chi, meaning farther to the left, look how large the p-value is going to be. Remember, p-value is the area after the test statistic. Right? Jim? Well, that's a good question. We'll get to that. So then, if you have a large disagreement, if you have O minus E squared is large, then chi squared is large. But what's that mean on the picture? Well, again, here's the distribution, right? But if chi squared is really large, what's the p-value going to be? P-value is going to be small. Now Jim asks the right question. He says, well, okay, how small or how large should it be? And your book says, if it's significantly large, again, what's that mean? Well, there's something called a significance level. What letter was that again? Alpha, right? See, somewhere here, the significance level is going to give me a critical value. Well, if my critical value, right, you compare the critical value. If I'm on this side of the critical value, I say, no, I'm not going to reject. But if I'm on that side of the critical value, I reject. That's all this is talking about. I think it's good to see it on the chi-squared picture because we haven't done that kind of distribution yet. Oh yeah, if p is low, the null must go. What is the null hypothesis? Here it is. That the distribution is as claimed. Okay, so remember, let me write that down. The distribution is as claimed. H1 then must be what? The distribution is not as claimed. Okay, so that's what the null hypothesis is that you're testing. Remember, null hypothesis can only test equality, right? That's why it's is. Is means equals. And you'll see when we do an example what you're testing. Your book gives this little chart which says exactly everything I just walked you through. So if you want a refresher on it, I said you don't need to write it all down. It's in there. Okay. This example's in your book, but I want to walk through it with you. Data set 1 in Appendix B includes weights from 40 selected males and also from 40 selected adult females. These weights were obtained as part of a national health examination survey. See what you think of this claim right here. When obtaining the weights of subjects, it is extremely important to actually weigh individuals instead of asking them to report their weights. Don't you think? Yeah. I'm not going to report my weight, exactly what it is, right? They want, when the health professionals are doing, they'll never ask you what your weight is. They're going to weigh you, right, when you walk in. Now, we have some data in the back. It says, by analyzing the last digits of weights, researchers can verify that the weights were obtained through actual measurements instead of being reported. How? How could you tell if the data came from people being weighed or people reporting their weights? Okay, if you don't want to tell me, talk about that with your neighbor for about 35 seconds here while I pause this. Talk with it to your neighbor. You don't have to share your weight with them. You don't have to. But at least talk about this question. Here's a weight, 201.5 pounds. So the last digit is 5. So now if you look at table 11.2 in your book, that's one of the data values, 5. Let me check that. Yeah, so all this data, they summarized on page 588. They made a frequency distribution. And yeah, they only looked at last digits. So somebody weighed 201.5 pounds, so they tallied that up as the last digit of 5. So now we're looking at all this here, and the instructions for this example say, test the claim, and that's always when I have these real long problems, that's the first thing I ask. What is the claim? Test the claim that the sample is from a population of weights in which the last digits do not occur with the same frequency. Okay, claim. The sample is from a population of weights in which the last digits do not occur with the same frequency. Wow, how am I going to do that? Well, I think what your book is going to do is they're going to say, look, we can make proportions if you want, or probabilities if you want, that certain digits are what they are, right? And then it says, based on the results, what can we conclude about the procedure used to obtain the weights? See, suppose you're looking at this and you say, hey, wait a minute, there were a lot of zeros. Then you might start to think, wait a minute, I don't think these were measured. And then you'd want to test that. The claim H1 that we're testing is that these proportions are not all equal. In other words, the distribution is not what? Uniform. Is not uniform. Although, you'll also be able to test, if you think that something's not normal, this is a way you can test it also. Okay? Although we have other tests for that too. And then I guess H0 is that, no, the proportions are all the same. Because remember, H0 is going to be we test equality. Now, how do we do it? Here's your table. Bless you. And by the way, there were 70 observed, so n equals 70. Oh, it was 80? Thank you. N equals 80? Okay. Yeah, I can go back. Okay, so back here. N equals 80, you told me, so I believe on that. And if that's true, I would use 70, too bad. But anyways, if that's true, how many should we expect for each one of these categories? Well, if it was 70, how many would you expect for each one of the categories? 7. Oh, I guess 80 works out well also, right? There's 10 categories. So what's E for any of these is 8. Did we ever get 8? I guess there we did. And there we did. So, right, E equals 80 times 1/10, because there's a 1 out of 10 chance of getting into any one of these frequencies. And this is for each category. See, this is the simplest kind of problem you can do, when the probability of each one of them is the same. But you can also do these problems where the probability is going to change. Then you have to compute E for each one separately. Okay? Now, I guess what I want eventually is I want O minus E. And then I want to square it. Right? So let's see. This is going to be 1, because it's a difference of 1, and then I square it. Here, what's this difference? 14 minus 8 is 6, so when I square it, I get 36. And you could have the technology do it, but to me, this is so easy that we may as well do this since we're doing the example so you can kind of understand what's happening. Okay? So there's O minus E squared. Now I'm going to have to divide by E and then add them all up. What was E? 8. All right? So since it's 8 for every one of them, that makes it even easier, right? But you could add this all up and get chi squared is, well, it's going to be something over 8. Let me add that up. Here's 40, 45, 65, 75, 85, 90. I got 90 over 8 when I added it all up. Well, no. What you're really supposed to do is do O minus E squared, yep, and then divide by E, and then add them up. But in this example, because it's 8 every single time, yeah, it's going to be 90 over 8. So I guess I just lucked out that these are all over 8, because it's equally likely. Equally likely are easier to do. Yeah, that's right. Okay, so there's my chi-squared value. Now, is that high or low? I don't know. We'll look at this in a second. Oh, we didn't check the requirements are satisfied. Randomly selected subjects. Frequency counts. We're counting frequency. And the expected frequency is 8. Remember, we computed E? It has to be bigger than 5, or else you shouldn't even do this test. Okay. Here's the claim. One of these probabilities is different from the others. By the way, just going back to the data, which one do you think might be different? Yeah, maybe the last digit 1 is different. Or maybe that's okay. Maybe it's not that different. Now, if you had 100 here, you'd start to say, wait a minute, something wrong with what's going on here. Right? Now, we'll see if that's a significant difference or not. Here's the same H0 and H1 that we came up with. Okay. Going through the steps, it says no significance is specified, so why don't we use alpha's 0.05? Okay? We've been doing that all year. Step 5, testing whether a uniform distribution. So we're going to use the goodness of fit test with chi-squared. See the next slide for the computation of the chi-squared test statistic. The test statistic, they say, is 11.25. Is that what we got? We got 11 and a quarter? Okay. It says alpha's 0.05, and, oh, how many degrees of freedom? They say 9. Do you understand why? There's 10 different categories we're looking at, right? That's K, but you subtract 1, you get 9. So again, okay, yeah, they did the same table we just did. They added all this up, and they used decimals, and they got 11.25. So I guess that's what we should get. Cool. Yeah, one other thing I wanted to say about this. Oh, the critical value. You're going to need to take out that card if you have it, and we can make sure that we can find the 16.919 on it. And this is what you'll use on the homework for next Tuesday. So I see let's see, 0.05 is the significance level. And if I go down to 9, I see the 16.919. You guys find that? So by the way, I guess what we're using here would be what's called the traditional method. Let me show you the picture, right? Here's the traditional method. In the traditional method, you plot the critical region. And the way we do it was this is the critical value, and it came from the 0.05. Now, we also computed chi-squared using our test statistic. This is the test statistic, and it's 11.25, which is over here. So that's why we failed to reject. So we failed to reject the fact, yeah, they might all be equally likely. Might just be that the one, you got a lot of them just because of your sample.
Small sample. And as you keep doing it.
Yeah, if we, what we think here is that if we kept doing this, then yeah, they'd be uniform. Okay. So they now just state that in English, what we just said. This goodness of fit test suggests that the last digits provide a reasonably good fit with the claimed distribution of equally likely frequencies. It seems like we actually weighed the subjects, not asking them what they weighed. Okay? So, that's the basic gist of this. There's one other thing I want to do, which is maybe look at the homework and just see, is there an example they do where the probabilities are different? Because if there is, I think I should show you that. So here, let's pull out the homework for a minute. If you skip ahead to page 594 and 595, let's see. Okay, like if you flip to page 596, problem 17 has an example like that. So I'll just make a comment on it here. Okay, the genetics problem. Blah, 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 blah. They tell me alpha is 0.05. It says, remember what I do? I don't read the whole thing. I go right to where it says, test the claim. Okay? So what's the claim in problem 17? That the frequencies, agree with these proportions. Now it's interesting. They say the proportions expected. That's what I remember studying in genetics. We did these things called Punnett squares, and we did all kinds of, we would take a look at alleles, they were called, and you want to test, hey, is this flower going to have this color or not? Is this fruit fly going to have these characteristics or not? And then we would actually observe them and do experiments, just like Mendel did years ago with beans. So, or the peas, thank you. So anyways, in this particular example, they're doing fruit flies. And they say there are 4 different characteristics you can look at. Now, the first one, for example, is red eye and normal wing. Okay? I don't care to list all these right now. I'm just going to call them category 1, 2, 3, 4. All right? So K here is 4. But then what they list is they list the frequencies. So what's the frequency? Well, it says 59 of these, 15 of these, 2 of these, 4 of these. Okay. And then they give you expected proportion. So they give me 9 out of 16. They give me 3 out of 16. They give me 3 out of 16. So let's see, that's 9 and 6 is 15 out of 16, so this one must be 1 out of 16. Right? What is it that they just gave you? That's the column I'd call E. Right? Those are the expected proportions. So in this problem, E is not the same everywhere. Okay? Well, I guess I better be careful. That's not E. That's P. Yeah, that's little p, the expected proportion. What is E? E equals N times P, right? So now I can compute what E is for each of these cases. And this is what the example didn't show you. Because in the example, it was easy. It was just everything's equally likely. But when you go ahead and do this, so let's see. If I do 59 times 9/16, there were 59 trials here. No, that's not what I want. No, I want N times P. So we need to know N. So N is going to be down here, the sum of all the frequencies. So let's see, 74 plus 6 looks like 80. Okay, if I can do that again. Actually, I don't even need a calculator for that one. 80 times 9/16 is 45, but we'll just do it. There's your 45. Okay. 80 times 3/16 is 15. And 80 times 1/16 is 5. So you need those E values. Now you can compare them to O. These are the observed frequencies. See that? Once you have O and you have E, now you can go ahead and kind of finish out the rest of the problem. But I wanted to make sure I showed you that because that's... Yep. For your test statistic, that's right. And you'll be fine from there. I just thought that this might be a little confusing at first until you've seen an example. Okay?